The morning of June 20th, 1943, Rechlin Experimental Airfield, Germany. Hauptmann Otto Kunert's hands paused over his clipboard as he watched the twin-engine Arado transport touch down, its cargo more valuable than gold intelligence that would alter Luftwaffe understanding of American bomber capabilities forever. Behind that transport sat evidence that would fundamentally challenge 3 years of carefully constructed assumptions about Allied industrial capacity and defensive doctrine. The Americans have built thousands of these machines, Kunert thought, studying the early morning light. Each one carries more defensive firepower than an entire Staffel of our bombers combined. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Through the operations window of Rechlin's main testing facility, Germany's premier evaluation center for captured Allied aircraft, Kunert could see the object of intense Wehrmacht interest sitting on the hardstand approximately 400 meters distant. A Boeing B-17 Flying Fortress, coded 7+8, had taught German fighter pilots brutal lessons about American defensive armament over the previous 6 months. But what arrived from Italy via Munich on this June morning represented something even more significant: the first intact Consolidated B-24 Liberator to fall into Luftwaffe hands in flyable condition. The Italians called her Blonde Bomber 2. American crews of the 343rd Bombardment Squadron, 98th Bomb Group, had known her as serial number 4, 1-23859. On February 20th, 1943, Lieutenant Don Story had mistaken the Sicilian airfield at Pacino for Malta after a raid on Naples, making an emergency landing that delivered America's second most important heavy bomber into Axis hands completely intact. Captain Giovanni Reina of the Regia Aeronautica had ferried the bomber to Catania Fontanarossa, then to Guidonia near Rome for evaluation. German demands for access to this prize created diplomatic tension between Axis partners. The Luftwaffe needed to understand this aircraft that was appearing over Europe in growing numbers. On June 19th, Reina departed Guidonia with German authorization, flying via Munich Riem to arrive at Rechlin the following day. The bomber carried temporary Italian civil registration IRAIN during the transit, a bureaucratic fiction that disguised a military intelligence operation of the highest priority. Kunert had supervised evaluation of dozens of captured Allied aircraft during his tenure at Rechlin's Department E3, the engine performance section. He had flown Spitfires, Hurricanes, Soviet Ilyushins, even the captured B-17 that still sat in Hangar 105. But the Liberator represented something qualitatively different from previous American bombers. Intelligence reports from frontline units described defensive firepower exceeding anything German fighter pilots had encountered in combat. 10 heavy machine guns of 50 caliber, each capable of firing 750 rounds per minute. Multiple powered turrets providing overlapping fields of fire across every approach angle. Formation tactics that multiplied this firepower across dozens of bombers simultaneously. The mathematics were staggering and disturbing. If accurate, a single B-24 carried more defensive armament than 3 German bombers combined. A formation of 27 Liberators, the standard American group strength, could bring 270 heavy machine guns to bear against attacking fighters. That concentration of firepower transformed daylight strategic bombing from theory into terrifying reality for Luftwaffe pilots who had to penetrate those defensive barriers to reach the bombers. Hans-Werner Lerche would become the test pilot most associated with captured Allied aircraft at Rechlin, though on this June morning he was conducting trials on a Hawker Typhoon at the satellite field in Rogentin. His eventual memoir, published decades after the war under the title Luftwaffe Test Pilot, Flying Captured Allied Aircraft of World War II, would provide the most detailed account of German evaluation procedures for enemy types. Lerche approached captured aircraft with scientific curiosity rather than ideological prejudice, a professional attitude that made him invaluable to the Luftwaffe's technical intelligence program. But first, Italian crews would provide the initial familiarization. Captain Reina and his mechanic Aldo Stagliano knew the Liberator intimately after 3 months, flying her from Italian bases. German technicians needed to learn American systems, American procedures, American design philosophy, embodied in 16 tons of aluminum and steel sitting on Rechlin's concrete. The Liberator represented Consolidated Aircraft's answer to Boeing's B-17, conceived in 1938 when the Army Air Corps requested a heavy bomber with greater range and payload than existing designs. Engineer David Davis had developed a wing suited specifically for long-range operations, a high aspect ratio design, offering 15% less drag than conventional wings. This Davis wing, mounted high on the shoulder, gave the Liberator speed and range exceeding the Fortress despite carrying a heavier bomb load. The first prototype flew in December 1939. By spring 1941, early models were reaching British forces under Lend-Lease agreements. The Royal Air Force christened the type Liberator, a name the Americans subsequently adopted. Early variants lacked self-sealing fuel tanks and heavy defensive armament, limiting their use to transport duties and anti-submarine patrol, where fighter opposition remained minimal. But combat experience drove rapid evolution. The B-24D model, which Blonde Bomber 2 represented, marked the first truly mass-produced variant suitable for strategic bombing operations. Turbocharged Pratt & Whitney R1830 engines, each producing 1,200 horsepower, gave the bomber speeds approaching 290 miles per hour at altitude. Maximum takeoff weight reached 59,524 pounds, making it one of the heaviest operational aircraft in the world. Range exceeded 2,000 miles with standard fuel load, allowing strikes deep into enemy territory from distant bases. But what captured German attention most intensely was the defensive armament. 10 Browning M2 machine guns of 50 caliber, positioned to provide coverage across nearly every approach angle a fighter might use. The nose carried flexible guns operated by bombardier and navigator. The dorsal turret, positioned just aft of the cockpit, mounted twin 50s in a powered Martin electric turret, rotating 360 degrees with excellent elevation traverse. The ventral position featured either a Sperry ball turret identical to the B-17's installation or a Bendix remotely operated turret, both providing complete lower hemisphere coverage. The tail turret housed twin 50s with clear field of fire directly aft. Waist positions on both sides of the fuselage carried flexible guns for beam defense. Later variants would increase this to 11 guns through addition of cheek positions in the nose. American production philosophy emphasized standardization and mass manufacturing. Every B-24 rolling off assembly lines in San Diego, Fort Worth, Tulsa, or Ford's massive Willow Run plant near Detroit featured identical defensive armament layouts, identical turret installations, identical fire control systems. This standardization meant replacement parts fit any aircraft regardless of production source. It meant gunners trained on one Liberator could operate any Liberator. It meant tactical doctrine developed for one squadron worked for all squadrons. German bomber production operated on entirely different principles. Each Heinkel, Dornier, or Junkers bomber featured unique defensive arrangements varying by production block and modification status. Defensive guns were often improvised additions rather than integrated design elements. Standardization remained a constant struggle as chronic shortages forced substitution of non-standard components. The contrast revealed fundamental differences in industrial philosophy and manufacturing capacity. Kunert watched as Italian and German crews gathered around Blonde Bomber 2 for the initial familiarization session. Captain Rayner would demonstrate startup procedures, explain instrument layouts, detail the handling characteristics that made the Liberator simultaneously capable and challenging to fly. American pilots described the B-24 as faster and longer ranged than the Fortress, but less forgiving of pilot error. The tricycle landing gear, a revolutionary feature for heavy bombers, simplified ground handling but required different techniques than conventional tailwheel designs. The high-mounted Davis wing created ground effect issues during landing that caught inexperienced pilots by surprise. The aircraft's tendency to snap into spins if mishandled at low speed demanded constant attention to airspeed and angle of attack. These handling peculiarities were already documented in captured flight manuals and pilot reports. What remained unknown was how the defensive armament actually performed under realistic combat conditions. Could the turrets track fast-moving targets effectively? Did the overlapping fields of fire create true all-aspect coverage, or were there exploitable blind spots? How accurate were the computing gun sights at estimating lead angles for deflection shots? What psychological effect did concentrated defensive fire have on attacking pilots? The test program would answer these questions through systematic evaluation. German fighter pilots would make simulated attack runs while Liberator gunners engaged them at various ranges. Ground observers would photograph the exercises and document approach angles, engagement distances, exposure times. The data would inform tactical bulletins distributed to every fighter unit facing American bomber formations. On June 20th, mechanical inspection began. German technicians removed inspection panels to examine internal structure and systems. The Liberator's construction revealed American manufacturing philosophy in stark detail. Riveted aluminum stressed skin construction distributed loads efficiently across the airframe. Modular subassemblies allowed rapid production and simplified maintenance. Interchangeable components meant parts from different production sources fit together without custom fitting. Every design choice reflected mass production requirements and logistics optimization. The 4 Pratt & Whitney twin Wasp engines mounted in nacelles beneath and ahead of the wing represented mature radial engine technology perfected through years of commercial aviation experience. 14 cylinders arranged in twin rows, each engine displacing 41.8 litres and producing 1,200 horsepower at rated altitude. Turbo superchargers maintained power output above 20,000 feet, where German fighters struggled for performance. The engines used automatic propeller governors and mixture controls, reducing pilot workload during combat when attention needed to focus on formation keeping and threat assessment. German aeronautical engineers marveled at the systematic approach to crew protection evident throughout the aircraft. Self-sealing fuel tanks lined with rubber compounds that swelled upon contact with aviation fuel, automatically sealing bullet holes and preventing catastrophic fuel loss. Armor plate protected pilot and co-pilot seats, positioned to stop rifle-caliber rounds and shell fragments from rear hemisphere attacks. The bomb bay featured armored bulkheads, separating the payload section from crew positions. Even the oxygen system incorporated redundancy, with multiple independent supply lines preventing single-point failures. These protection systems added substantial weight. German engineers calculated approximately 500 kilograms of armor plate, self-sealing materials, and redundant systems, but American doctrine treated trained crews as more valuable than aircraft. Keeping experienced airmen alive through multiple combat missions justified the performance penalty of protection systems. This philosophy contrasted sharply with German practice, where weight savings often took priority over crew survival. The defensive armament received the most intensive examination. Each turret was disassembled, photographed, measured, and tested for mechanical operation. The Martin electric dorsal turret impressed German engineers with its sophisticated design. The entire gun platform rotated smoothly on ball bearings through full 360 traverse. Elevation covered 90 degrees from horizontal, allowing engagement of targets from directly ahead to directly above. The twin 50 caliber Brownings mounted in the turret could fire independently or simultaneously, providing either sustained fire or concentrated bursts. A computing gun sight helped the gunner calculate lead angles for moving targets, though accuracy still depended heavily on the gunner's skill and experience. The Sperry Ball turret on this particular aircraft represented engineering ingenuity, addressing a difficult problem, providing complete lower hemisphere coverage in a retractable installation. The gunner entered the turret from inside the fuselage, curling into fetal position in the cramped sphere barely 3 feet in diameter. Ammunition feeds entered from above through the rotation mechanism. The optical gun sight mounted, directly in front of the gunner's face, requiring him to press his oxygen mask against the eyepiece. Twin 50s fired through ports that allowed engagement across the entire lower hemisphere, with no blind spots below the aircraft. The physical demands were severe. Ball turret gunners needed to be small in stature, typically under 5 feet, 8 inches tall, and weighing less than 160 pounds. The position was too cramped for a parachute, creating psychological stress that some gunners never overcame. Temperatures at altitude reached 40 degrees below 0 Fahrenheit. Frostbite was common despite electrically heated suits. The gunner remained suspended beneath the aircraft for entire missions lasting 6 to 8 hours, unable to move or stretch cramped muscles. If the turret mechanism jammed with the guns pointed downward during landing, the gunner faced being crushed as the fuselage settled onto the runway. Yet the ball turret was devastatingly effective at its intended purpose. No angle of approach from below escaped its field of fire. German pilots quickly learned through bitter experience that attacking from beneath a B-24 formation meant exposing themselves to concentrated fire from multiple ball turrets, each one tracking their approach with mechanical precision and opening fire at maximum effective range. The waist gun positions represented more conventional, flexible installations. Gunners stood at open windows along the fuselage midsection, operating 50 caliber Brownings mounted on ring sockets that allowed wide traverse in azimuth and elevation. The open windows exposed gunners to hurricane-force winds, sub-zero temperatures, and deafening engine noise. Communication was nearly impossible without the intercom system. Oxygen deprivation remained a constant threat if mask seals failed or lines disconnected during violent maneuvering, but the waist positions provided critical beam defense, covering approach angles that neither dorsal turret nor ball turret could engage effectively. 2 gunners, one on each side of the fuselage, could concentrate fire on targets approaching from 9 o'clock or 3 o'clock positions. The staggered positioning prevented the gunners from interfering with each other's movement while maximizing coverage angles. June 21st brought the first ground engine runs. Captain Rayner occupied the left seat, walking German observers through startup procedures and instrument monitoring. The 4 twin Wasps came to life with characteristic radial engine sound, a deep, powerful rumble that vibrated through the airframe. Turbochargers whistled as boost pressure built. Propeller governors adjusted blade pitch automatically to maintain selected RPM. The synchronized engine controls reduced pilot workload dramatically compared to German bombers where pilots manually adjusted throttle, mixture, propeller pitch, and supercharger settings for each engine independently. On June 22nd, taxi tests began. The tricycle landing gear configuration made ground handling surprisingly easy. Unlike tailwheel aircraft that required S-turns during taxi to see ahead past the nose, the Liberator's nose wheel arrangement provided excellent forward visibility. Steering was accomplished through differential braking and nose wheel steering linked to the rudder pedals. The wide-track main gear gave excellent stability during ground operations, but the 4th test flight on June 23rd produced disaster that would ground Blonde Bomber 2 for months. German test pilot Werner Baumbach, who had trained on the Liberator under Rayner's supervision, made what appeared to be a normal landing approach. But the hard, sun-baked grass runway at Rechlin caught the nose wheel incorrectly during the landing roll. The nose gear collapsed under side loads it wasn't designed to withstand, driving the nose into the earth and causing substantial structural damage to the forward fuselage. Italian crews were horrified. This was their aircraft, entrusted to German care through diplomatic negotiations. Now it sat broken on a German runway, likely to remain there for months while repair parts were manufactured from scratch. German technicians assured them the damage could be repaired, but obtaining replacement nose gear components would require either fabrication from drawings or scavenging parts from another captured Liberator, which didn't yet exist in German hands. While repairs proceeded through July and August, intelligence reports from combat units provided disturbing context for the test program. American bomber formations over Europe were growing steadily larger and more sophisticated. The tight defensive boxes that multiplied individual bomber firepower across entire formations were becoming standard doctrine. Fighter attacks that had been reasonably successful in early 1943 were producing catastrophic losses by summer. On July 7th, 373 B-24s and 956 B-17s attacked synthetic oil plants deep in Germany, protected by 756 long-range escort fighters. German defenders threw everything available against this massive formation. Messerschmitt 109s, Focke-Wulf 190s, even twin-engine Messerschmitt 1-10 heavy fighters mounting batteries of cannon specifically for bomber destruction. The battle lasted hours as formations penetrated to their targets and fought their way back to England. Fighter pilot reports from that mission described the same terrifying reality across every engagement. The defensive firepower from American bomber formations was overwhelming. A pilot making a head-on attack faced fire from multiple bombers simultaneously, dozens of 50-caliber machine guns throwing hundreds of rounds per second into his approach corridor. Breaking through that curtain of fire required exceptional nerve, perfect timing, and a considerable luck. Many pilots broke off their attacks prematurely, survival instinct overcoming tactical discipline as tracers filled the sky ahead. Even successful attacks often proved futile. A Focke-Wulf 190 pilot might close to point-blank range, fire his cannons directly into a bomber's wing or fuselage, see his strikes impact, and watch the bomber continue flying. American self-sealing fuel tanks prevented the catastrophic fires that doomed German aircraft hit in the wings. Redundant systems meant single failures rarely proved fatal. Structural strength allowed Liberators and Fortresses to absorb damage that would tear apart German bombers, continuing toward targets despite horrific battle damage. Hauptmann Werner Vorbrugge, commanding 3rd Squadron of Fighter Wing 3, filed an after-action report following the July 7th mission that captured the frustration shared by fighter pilots across all units defending the Reich. We attacked the Liberator formation from 11 o'clock high in accordance with established doctrine. The first pass achieved surprise, and several bombers appeared heavily damaged, but as we closed for follow-up attacks, the defensive fire became overwhelming. Every bomber in the formation was firing at our Staffel simultaneously. The tracer streams filled the air so completely that continuing the attack seemed suicidal. I observed 2 of my pilots break off their runs before reaching firing range. I cannot blame them. Flying into that defensive fire requires extraordinary courage, and even successful attacks often fail to destroy the target. These tactical realities worried German planners who understood the strategic implications. If American bombers could survive to reach their targets despite determined fighter opposition, if they could absorb battle damage and continue flying, if they could deliver heavy bomb loads with acceptable accuracy while defending themselves effectively, then the entire concept of daytime, strategic bombing, abandoned by both Germany and Britain after experiencing unsustainable losses, had been vindicated by American industrial capacity and tactical innovation. By early September, repairs to Blonde Bomber 2 were complete. German technicians had fabricated new nose gear components using specifications derived from technical drawings and measurements of the damaged parts. The bomber received new German camouflage, overall dark green, replacing the desert pink scheme carried from North African operations. German national insignia replaced American markings. The charming blonde pin-up that gave the bomber its name disappeared beneath Wehrmacht paint. Hans-Werner Lerche finally got his opportunity to fly the Liberator in September 1943. His approach to unfamiliar aircraft reflected systematic methodology developed through years of test flying. First, study all available documentation, captured flight manuals, pilot reports, intelligence summaries, anything that might provide insight into the aircraft's characteristics. Second, conduct thorough walk-around inspection, examining every accessible system and control surface. Third, sit in the cockpit for extended periods, memorizing instrument layouts and control positions without starting engines. Fourth, conduct taxi tests to develop feel for ground handling. Only then, attempt first flight. Lurch had no qualified instructor, no checkout program, no training syllabus. He learned by observation and experimentation, making educated guesses about system operation and testing his assumptions carefully at altitude, where mistakes wouldn't prove immediately fatal. The instrument layout differed significantly from German practice in both arrangement and philosophy. American designers favored centralized panels with standardized gauge positions consistent across different aircraft types, allowing pilots to transition between aircraft more easily. Circuit breakers replaced fuses in the electrical system, providing resettable protection that simplified troubleshooting. Hydraulic pressure indicators used different scales calibrated in pounds per square inch, rather than kilograms per square centimeter. The throttle quadrant, operated with reversed logic compared to German aircraft forward motion, increased power rather than decreased it. This fundamental difference required conscious mental adjustment every time Lerche touched the throttles. Push forward for more power, pull back for less power. The opposite of every instinct developed flying German types. First flight came on a clear September morning with excellent visibility and light winds conditions that minimized risk for testing an unfamiliar aircraft. Lerche completed his pre-flight inspection with characteristic thoroughness, checking control surface movement, examining landing gear mechanisms, verifying fluid levels. He climbed into the left seat and reviewed his mental checklist one final time. Fuel. Selectors, main tanks. Mixture, rich. Propellers, full forward. Throttles, closed. Master switches, on. The startup sequence followed procedures Captain Rayner had demonstrated months earlier. Engage starter on engine number 1. Watch oil pressure rise. Monitor exhaust gas temperature. Advance throttle slightly as engine catches. Repeat for engines 2, 3, and 4. The 4 twin Wasps settled into smooth idle, instruments showing normal indications across all parameters. Lerche released parking brake and began taxi toward the active runway, testing brakes and steering during the taxi. The tricycle gear made ground operations remarkably easy compared to tailwheel fighters that required constant attention to prevent ground loops. At the runway threshold, Lerche performed his takeoff checklist. Flight controls, free and correct. Trim tabs, set for takeoff. Flaps, 10 degrees. Fuel. Main tank selected, boost pumps on. Propellers, full forward. Mixture, auto-rich. Turbochargers, as are required for altitude. He aligned the aircraft with the runway center line, locked the tail wheel, and smoothly advanced all 4 throttles to take off power. The Liberator accelerated steadily down the concrete runway, the 4 1200 horsepower engines producing combined thrust exceeding 4,800 horsepower. At approximately 80 miles per hour indicated airspeed, Lerche applied gentle back pressure on the control column. The nose wheel lifted smoothly off the runway. At 95 miles per hour, the main wheels left the ground and the bomber transitioned to flight. Lerche immediately recognized the flight characteristics pilots had described in captured reports. The Liberator flew with surprising stability for such a large aircraft, responding to control inputs with predictable docility. Slight forward pressure on the control column produced gentle descent. Slight back pressure initiated climb. The aircraft tracked straight and level with minimal pilot. Input, a characteristic that would make formation flying less demanding than in aircraft requiring constant correction to maintain position. But Lerche also noted the less pleasant characteristics. The high-mounted Davis wing created substantial dihedral effect, making the bomber sensitive to yaw-induced roll. Any sideslip produced strong rolling moment that required prompt rudder correction. At slow speeds approaching stall, the wing generated irregular buffeting that could transition rapidly into departure from controlled flight if the pilot failed to recognize warning signs. The tricycle landing gear, while excellent for ground handling, created different flare characteristics during landing. The nose needed to stay slightly low during touchdown to prevent ballooning, a counterintuitive technique for pilots trained on tail-wheel aircraft. Lerche spent an hour exploring the flight envelope within safe parameters. He climbed to 15,000 feet and conducted gentle turns, noting the roll rate and coordination required to prevent adverse yaw. He slowed to approach speeds and felt the wing buffet develop, carefully staying well above actual stall speed. He advanced throttles to maximum continuous power and felt the bomber accelerate smoothly, the turbo superchargers maintaining sea-level power output despite altitude. He shut down one engine and trimmed for single-engine flight, confirming that the Liberator remained fully controllable on 3 engines' critical capability for surviving battle damage. Landing required careful attention to the unique characteristics. Lerche configured the aircraft with full flaps and appropriate power setting to maintain a stabilized approach. He aimed for the runway threshold at 95 miles per hour indicated, slightly higher than minimum approach speed to provide safety margin. Over the threshold, he reduced power smoothly and transitioned to landing attitude, holding the nose slightly low until the main wheels contacted. Only then did he allow the nose wheel to settle gently onto the runway. The landing was smooth and unremarkable, exactly what good test flying should produce. Lerche's initial evaluation report praised the Liberator's docile handling, excellent visibility from the cockpit, sophisticated engine controls that reduced pilot workload, and effective landing gear design. But he also noted vulnerabilities that would interest fighter tacticians. The high-mounted wing created a significant blind spot directly above the aircraft where the dorsal turret had limited elevation traverse. Attacks from 12 o'clock high might avoid some defensive fire if timed correctly. The transition from level flight to defensive maneuvers appeared sluggish, suggesting that bomber pilots couldn't evade attacks through violent maneuvering as fighter pilots could. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content, like this. Thank you for watching. I'll now continue with part 2 of the script, where I'll cover the tactical testing, the psychological impact on German pilots, and the broader implications of what Rechlin's analysis revealed about American industrial capacity and bomber doctrine. The tactical evaluation program began in earnest during October 1943. Rechlin's test protocols required systematic assessment of every captured aircraft's combat capabilities through realistic engagement scenarios. For bombers, this meant determining defensive effectiveness against the fighters that would attack them in actual combat. German fighter pilots from operational units were temporarily assigned to Rechlin specifically for these evaluations. They brought recent combat experience attacking American bomber formations over Germany, France, and the Low Countries. Their perspective was invaluable. They knew which approach angles worked, which tactics failed, which psychological pressures affected decision-making during attacks. These pilots would make simulated attack runs against the Liberator while it flew straight and level or performed evasive maneuvers, exactly as bombers did when under fighter attack. Oberfeldwebel Karl Heinemann arrived at Rechlin in mid-October with 73 combat missions logged and 11 confirmed victories, 8 of them American heavy bombers. He had survived encounters that killed many of his squadron mates. His Focke-Wulf 190 bore scars from defensive fire that had punched holes through wings, tail and fuselage, without striking anything vital enough to bring him down. Luck and skill in roughly equal measure had kept him alive through the brutal summer of 1943, when German fighter losses approached unsustainable levels. Heinemann's assignment to Rechlin provided temporary respite from the daily missions that were steadily depleting experienced pilots from every fighter unit defending the Reich. But the assignment also reminded him why those missions had become so costly. Walking around the captured Liberator on his first morning at the test center, examining the gun positions and turret installations, Heinemann felt the familiar cold knot of anxiety that preceded every mission. 10 guns, he said to Hauptmann Kunert, who was conducting the briefing. I count 10 50 caliber positions, and this is just one bomber. Correct, Kunert confirmed. The standard combat box formation contains 27 aircraft. That means 270 heavy machine guns providing interlocking defensive fire. Heinemann did the mental arithmetic that every German fighter pilot learned through painful experience. Each gun fired approximately 750 rounds per minute. 10 guns per bomber meant 7,500 rounds per minute per aircraft. 27 bombers meant over 200,000 rounds per minute across the entire formation. Translated to rounds per, Second, for better understanding of immediate tactical effects, more than 3,000 heavy machine gun bullets entering the surrounding airspace every single second. How do they expect us to penetrate that? Heinemann asked, though he already knew the answer. They expected pilots to attack anyway, to press through the defensive fire despite the odds, to destroy bombers or die trying. There was no other option. The American bombing campaign was systematically destroying German industrial capacity. Fighter pilots had to stop the bombers, or Germany would lose the war through attrition of its manufacturing base. The evaluation protocol called for Heinemann to make attack runs from various angles, while the Liberator's turrets tracked his approach and simulated engagement. No live ammunition would be fired too dangerous and wasteful of scarce resources. But German gunners trained on the Liberator's systems would operate the turrets exactly as they would in combat, tracking the attacking fighter and calling out when they had firing solution. Ground observers with theodolites and stopwatches would measure approach angles, closure rates, time exposed to defensive fire, and assess whether the attack would likely succeed under actual combat conditions. Heinemann climbed into his Focke-Wulf 190A-5 for the first simulated engagement. The 190 was Germany's premier fighter bomber, a rugged interceptor capable of withstanding substantial battle damage while delivering devastating firepower from its stable gun platform. This particular aircraft mounted two 13mm MG-131 machine guns in the cowling and four 20mm MG-151 cannons, two in the wing roots, two in underwing gondolas. Total armament weight exceeded 300 kilograms, more than enough firepower to destroy any bomber with properly placed hits. The test protocol specified attacking from 6 o'clock level, directly behind the Plef Liberator, the traditional approach that had worked well against earlier Allied bombers with limited defensive armament. Heinemann climbed to the test altitude of 15,000 feet and positioned his fighter 3 kilometers behind and slightly above the bomber, which flew straight and level at 180 miles per hour. He advanced throttles to maximum continuous power and began his attack run. The Liberator grew steadily larger in his gun sight as closure rate built toward typical engagement speeds. At 1,000 meters range, the bomber's tail turret swung directly toward him and began tracking. The twin 50s pointed straight at his fighter, following his approach with mechanical precision. "Tail gunner has firing solution," crackled over the radio. "Range 1,000 meters. You are engaged." Heinemann pressed his attack, just as he would in actual combat. At 800 meters, the distinctive shape of the Liberator's fuselage and wings filled his gun sight. He noted the tail turret maintaining perfect tracking, despite his attempt to jink slightly left and right to complicate the gunner's aim. "Dorsal turret engaging," came another radio call. "Range 800 meters." Now 2 turrets were tracking him, 4 50 caliber machine guns concentrating fire along his approach path. In actual combat, both gunners would be firing continuously, throwing 30 rounds per second toward his fighter. The concentration of fire would create a visible stream of tracers. Every 5th round was tracer for aiming correction that appeared as solid lines connecting the bomber to his fighter. At 600 meters, Heinemann's own cannons would come into effective range. He centered the Liberator in his sight and mentally calculated lead angle for deflection, shot at the rapidly decreasing range. But the dispassionate voice continued, providing tactical assessment. "Waist gunners engaging. Range 600 meters. 4 guns tracking. 4 guns had become 6, 60 rounds per second. In the 3 seconds it would take to close from 600 meters to 300 meters, the Liberator's gunners would fire approximately 180 heavy machine gun bullets into the cone of space his fighter had to traverse. Even accounting for the difficulty of deflection shooting at high closure rates, probability of multiple hits approached certainty. At 300 meters, Heinemann would normally break away to avoid collision. The 3-second firing window from 600 to 300 meters represented the only opportunity to deliver effective cannon fire. 3 seconds during which 6 heavy machine guns poured fire toward his fighter. 3 seconds that determined whether he scored hits sufficient to destroy the bomber or merely damaged it enough to slow its return to England. 3 seconds that decided whether he lived or died. Break away. ordered the test controller. Evaluation complete. Heinemann pulled hard left and dove away from the bomber, his heart pounding despite the absence of actual danger. No live ammunition had been fired. No bullets had passed within meters of his canopy. Yet the psychological impact of having 6 gun positions tracking his approach, knowing that in combat those guns would be firing continuously, created visceral stress that affected decision-making and performance. He rejoined the bomber for the next approach, this time from 11 o'clock high, diving from above and ahead in the frontal attack profile that German aces had pioneered as the most effective tactic against American heavy bombers. The head-on pass offered the smallest target aspect, minimized time exposed to defensive fire, and allowed the attacking pilot to aim at a relatively stationary target growing larger in his gun sight. Heinemann climbed to 20,000 feet and positioned himself 4 kilometers ahead of the bomber's track. He rolled inverted and pulled through into a steep dive, building speed toward 400 miles per hour as he plummeted toward the Liberator approaching from below. The combined closure rate exceeded 600 miles per hour, more than 800 feet per second. The entire engagement from first detection to passing the bomber would last perhaps 5 seconds. At 1,000 meters range, slightly more than 1 second before firing distance, the bomber's nose turret swung toward him. On this particular B-24D model, the nose carried only flexible guns operated by bombardier and navigator, not the powered turret that would appear on later variants. But the dorsal turret could rotate forward to add its 2 guns to the defensive barrage. Nose guns engaging, range 1,000 meters. Dorsal turret engaging forward, 4 guns tracking. Heinemann watched the bomber expand rapidly in his gun sight as the dive continued. His fighter was now slightly nose down to the bomber's flight path, creating a deflection angle that required lead. Calculation. Too much lead and his cannon shells would pass ahead of the target. Too little lead and they would pass behind. Perfect lead required split-second timing at these combined speeds. At 400 meters, he would open fire, maximum effective range for his cannons given the high closure speed and deflection angle. The firing window would last perhaps 1 second before he passed over the bomber and broke away to avoid collision. 1 second to aim, fire, observe strikes, and initiate breakaway. 1 second to destroy or damage the bomber sufficiently to remove it from formation. Range 400 meters. You are in firing envelope. But so were the bomber's defensive gunners, 4 50-caliber machine guns tracking his dive, leading his fighter, waiting for the moment to open fire. In actual combat, the nose gunners would have been firing from first detection at 1,000 meters, throwing rounds into his approach path and hoping for lucky hits. The dorsal turret gunner, more skilled and better equipped with computing gun sight, would wait until range closed to 400 or 500 meters, where hit probability increased dramatically. Breakaway. Heinemann pulled hard on the stick, vectoring away from the bomber at maximum G-loading his fighter could sustain. The Focke-Wulf's rugged airframe handled the stress easily, but Heinemann felt the crushing pressure of 7 Gs compressing his body into the seat and draining blood from his brain toward his legs. His vision began to grey at the edges before he relaxed back pressure slightly and the tunnel vision cleared. The test controller's voice provided assessment. Attack run successful from tactical standpoint. Fighter pilot maintained proper closure rate and achieved firing position. However, fighter was exposed to defensive fire for approximately 2 seconds from 400 meters range. In combat conditions, probability of fighter sustaining damage approaches 70%. Probability of fatal damage approximately 20% based on analysis of actual combat engagement data. 20%. 1 chance in 5 that a perfectly executed frontal attack would result in the fighter being destroyed by defensive fire from a single bomber. And that calculation assumed only 1 bomber engaging in actual combat. Multiple bombers in formation would concentrate fire on the attacking fighter, dramatically increasing hit probability. 3 bombers engaging simultaneously meant 60% chance of fatal damage. 5 bombers meant near certain destruction. The mathematics explained why German fighter losses had increased so dramatically since spring 1943, when American bomber formations reached the strength and sophistication to implement proper defensive box tactics. Every attack run was essentially a calculated risk, gambling pilot's life against probability of destroying bomber before defensive fire destroyed the fighter. Heinemann made attack runs from below, from beam positions, from high angles, from low angles. Each approach revealed the same fundamental reality. The Liberator's defensive coverage left few exploitable gaps. The ball turret provided complete lower hemisphere coverage with no blind spots. The waist positions covered beam attacks. The tail turret and dorsal turret together covered the rear hemisphere. Only the area directly above and slightly ahead offered any reduction in defensive firepower, and even that advantage disappeared if multiple bombers in formation could bring their guns to bear. After completing his evaluation flights, Heinemann filed a tactical report that would be distributed to fighter units across the Reich. His conclusions were stark and disturbing. The B-24 Liberator possesses defensive firepower superior to any bomber previously encountered. The 1050 caliber machine guns provide overlapping coverage across all approach angles. Frontal attacks remain the most viable tactic, but success requires exceptional nerve to press through defensive fire at point-blank range. Attacks from rear hemisphere should be avoided as suicidal, except when bomber has been separated from formation and damaged to the point of limited defensive capability. The greatest threat is not individual Liberator defensive firepower, but the multiplied effect when attacking formations of 20 or more aircraft. Under those conditions, successful attack requires accepting high probability of fighter loss even if bomber is destroyed. Other experienced pilots completing evaluations at Rechlin during October and November filed similar reports. Major Gunther Specht, an ace with 54 confirmed victories, wrote with unusual candor about the psychological impact of attacking heavily defended bomber formations. The American defensive system has transformed bomber interception from a tactical problem into a psychological test. Every pilot knows intellectually that penetrating the defensive fire is possible, that proper approach angles and aggressive flying can achieve successful attacks. But knowing this, intellectually, differs profoundly from forcing oneself to actually fly directly into concentrated machine gun fire from dozens of bombers simultaneously. The tracer streams create visual impression of solid walls of fire. The instinct for self-preservation screams to break away, to abandon the attack, to survive. Overcoming that instinct requires constant mental discipline and extraordinary courage. Many pilots, particularly those with limited combat experience, break off attacks prematurely before reaching effective firing range. This is not cowardice, it is normal human response to overwhelming sensory input suggesting immediate death. The psychological dimension of bomber defense had not been anticipated by pre-war German doctrine. Luftwaffe theorists had assumed that determined fighter pilots could successfully attack bomber formations through superior speed, maneuverability, and firepower. The calculations had focused on physical capabilities, closure rates, firing windows, armor penetration, damage models. What the calculations had not accounted for was the human factor, the mental stress of deliberately flying into defensive fire so intense that survival seemed impossible. American bomber crews understood this psychological warfare intuitively. Gunners were trained to open fire at maximum range regardless of hit probability. The goal was not necessarily to destroy attacking fighters, though that was always welcome, but to create visual and psychological effects that would discourage attacks or cause pilots to break off prematurely. A bomber formation firing hundreds of heavy machine guns simultaneously created spectacular display of tracer fire that filled the sky with visible streams of bullets. Every fifth round was tracer, meaning visual impression showed only 20% of actual rounds being fired. The real bullet density was 5 times greater than what attacking pilots could see. German fighter pilots described flying through this defensive fire using terms that revealed profound psychological impact: flying into a wall of steel, swimming through fire, tunneling through tracers. The metaphors consistently emphasized overwhelming visual and sensory overload that made rational calculation nearly impossible. Pilots fell back on training, discipline, and sheer determination to continue attacks despite every instinct screaming to break away. By late November 1943, testing of Blonde Bomber 2 was essentially complete. German engineers and tactical analysts had learned everything useful from the captured Liberator. They understood its defensive systems, its flight characteristics, its strengths and weaknesses. The intelligence gathered at Rechlin was compiled into detailed technical reports and tactical bulletins distributed throughout the Luftwaffe. But this intelligence could not change the fundamental arithmetic that determined strategic outcomes. Understanding the B-24's capabilities didn't eliminate those capabilities or create effective counters when the resources to implement such counters didn't exist. German fighters could attack American bombers more effectively using knowledge gained from Rechlin's evaluations, but American bombers kept coming in, ever-increasing numbers that made tactical improvements irrelevant. The production statistics told the story that German intelligence analysts understood but could do nothing to change. Consolidated Aircraft Corporation, Douglas Aircraft, Ford Motor Company, and North American Aviation together produced more than 18,000 B-24 Liberators between 1940 and 1945. Peak production in 1944 saw Ford's Willow Run plant alone, building B-24s at rate exceeding 360 aircraft per month, more than 12 bombers per day from a single factory, one aircraft every 2 hours, around the clock, 7 days per week. The numbers seemed impossible to German observers who understood aircraft manufacturing, yet multiple intelligence sources confirmed the production rates through different methods. Photographic reconnaissance of American factories showing hundreds of bombers on hardstands awaiting delivery, signals intelligence intercepts discussing production schedules, interrogations of captured American aircrews, who described the constant flow of replacement aircraft to operational units. American industrial capacity operated on scale that German industry could never match. The reasons were both simple and complex. Geography protected American factories from bombing raids that disrupted German production. Resources flowed freely across American territory without interdiction by enemy forces. Manpower remained abundant as women entered industrial workforce in unprecedented numbers. Most fundamentally, American economic system and industrial organization proved more adaptable to total war mobilization than German systems hampered by competing bureaucracies and ideological rigidity. The B-24 symbolized this industrial advantage. Each bomber contained approximately 45,000 individual parts manufactured by hundreds of subcontractors across the United States. 4 Pratt & Whitney engines producing 1,200 horsepower each. Miles of electrical wiring connecting systems. Thousands of pounds of aluminum formed into airframe structures, that formidable defensive armament of 10 heavy machine guns with thousands of rounds of ammunition. Self-sealing fuel tanks incorporating rubber compounds from natural and synthetic sources. Armor plate protecting crew positions. Turrets with sophisticated mechanisms for powered rotation and elevation. Building 18,000 of these complex machines while simultaneously producing fighters, transports, trainers, and every other type of military aircraft required industrial organization on unprecedented scale. American factories implemented mass production techniques pioneered by automotive industry, using standardized components, interchangeable parts, and assembly line methodology. Semi-skilled workers could build complex aircraft using jigs, fixtures, and detailed instructions, reducing reliance on scarce craftsmen. German aircraft production operated on fundamentally different principles. Each airplane required substantial hand-fitting of components by skilled workers. Standardization remained elusive as chronic shortages forced substitution of non-standard parts. Factory organization emphasized small batch production by craftsmen rather than mass production by semi-skilled labor. These methods produced excellent aircraft, but in quantities insufficient to compete with American industrial output. Hauptmann Kunert understood these realities as he compiled final reports on the Liberator evaluation program. The captured B-24 had taught Luftwaffe pilots how to attack American bombers more effectively. But no amount of tactical knowledge could overcome the fundamental arithmetic of industrial capacity. For every Liberator shot down over Germany, American factories built 5 replacements. For every German fighter pilot who mastered techniques for penetrating bomber defensive fire, 10 novice pilots died on their first or second mission before learning effective tactics. The war of attrition was being fought on multiple levels simultaneously. In the air, German fighters battled American bombers and escorts, trading unsustainable losses for modest reductions in bombing effectiveness. On the ground, German factories struggled to maintain production under constant Allied bombing that destroyed facilities, killed workers, and disrupted transportation networks. In training schools, German flight instructors tried to compress multi-year training programs into months to replace pilot losses, producing aviators with marginal skills who died quickly in combat against experienced American crews. By December 1943, experienced Luftwaffe officers privately acknowledged that Germany was losing the air war through simple arithmetic. American industrial capacity exceeded German capacity by factors that made long-term German victory impossible through any realistic scenario. The strategic bombing campaign would continue regardless of German defensive efforts. The bomber fleets would grow larger. The fighter escorts would become more numerous and capable. The tactical sophistication would increase as Americans learned from combat experience and adjusted their doctrine. The only question was timing. How long could German forces continue fighting against increasingly overwhelming material disadvantage before collapse became inevitable? Blonde bomber. 2 eventually departed Rechlin for assignment to Kampfgeschwader 200, the Luftwaffe's Special Operations Unit, that operated captured Allied aircraft for clandestine missions and intelligence gathering. The bomber received German military codes and camouflage scheme appropriate for nighttime penetration of Allied airspace. Records of its operational service with KG-200 were lost or destroyed during the war's final months, but several B-24s flew special missions for the unit throughout 1944 before Allied air superiority made such operations impossibly dangerous. The evaluation program at Rechlin continued through 1944, as additional Liberators fell into German hands through combat damage and forced landings. Each captured bomber provided opportunity for further study and tactical refinement, but the fundamental lessons remained unchanged from those learned examining the first intact B-24 in June 1943. American heavy bombers possessed defensive firepower that transformed daylight strategic bombing from theoretical concept into the devastating reality. The 10 50 caliber machine guns on each Liberator, multiplied across formations of dozens of aircraft, created defensive barriers that German fighters could only penetrate by accepting catastrophic losses. Self-sealing fuel tanks, armor protection, and rugged construction meant American bombers could survive battle damage that would destroy German aircraft. Most significantly, American industrial capacity could replace combat losses faster than German forces could inflict them. German fighter pilots continued attacking American bomber formations throughout 1944, despite knowing the odds. Many died in the defensive fire they had learned to expect and fear. Others survived through combination of skill, luck, and determination that defied probability. Some aces achieved remarkable success, developing personal techniques that allowed them to destroy multiple bombers despite overwhelming defensive firepower. But individual heroism and tactical excellence could not compensate for industrial disparity and numerical inferiority. By spring 1944, American fighters with drop tanks accompanied bomber formations to targets deep inside Germany, eliminating the sanctuary where German fighters had previously operated without facing enemy interceptors. The P-51 Mustang, with range exceeding the bombers it escorted and performance superior to German fighters, fundamentally changed the tactical equation. German fighter pilots now faced the impossible task of penetrating bomber defensive fire, while simultaneously defending themselves against American escorts that outnumbered them and possessed performance advantages. Loss rates climbed to unsustainable levels. Experienced pilots died at rates that training programs could not replace. Average experience levels declined as novices replaced veterans, creating downward spiral where declining pilot quality led to higher losses that further reduced pilot quality. The captured Liberator at Rechlin had revealed everything German forces needed to know about American bomber capabilities. The intelligence was accurate, detailed, and tactically useful. But intelligence alone could not create resources that didn't exist. It could not manufacture fighters faster than American industry-produced bombers. It could not train replacement pilots more quickly than combat-killed experienced aviators. It could not transport fuel that Allied bombing had prevented from being refined. It could not rebuild factories that strategic bombing had destroyed. Hans Werner Lurch survived the war and published his memoirs decades later, providing detailed accounts of flying captured Allied aircraft, including multiple B-24 variants. His professional assessment, written with the perspective of years and freed from wartime propaganda constraints, acknowledged what he and other test pilots had understood at the time. The Liberator was an excellent bomber, well suited to tow its intended mission of long-range strategic bombing. Its defensive armament was among the most comprehensive I encountered on any Allied aircraft. The real secret was not the individual aircraft's capabilities, but the American system that could produce 18,000 of them while simultaneously building every other type of military equipment needed to fight a global war on multiple fronts. We could study captured Liberators and learn their characteristics. We could develop tactics to attack them more effectively. We could train our pilots in the specific techniques required to penetrate their defensive fire. But we could not match the industrial output that made American strategic bombing inevitable, regardless of German defensive efforts. The final American bombing raid on Rechlin came on April 10, 1945. 11 B-17s and 159 B-24s from the 8th Air Force targeted airfields used by German jet fighters, including Rechlin's test facilities. The massive formation approached at high altitude, protected by hundreds of fighter escorts. German defences were minimal, fuel shortages had grounded most fighters, and the few that could fly lacked ammunition for sustained combat. The bombing was devastatingly accurate. High explosive bombs destroyed runways, hangars, workshops, and aircraft dispersed around the field. What the bombs missed, German forces destroyed themselves to prevent capture by Soviet troops advancing from the east. On May 2nd, Soviet forces occupied Rechlin and found ruins where Germany's premier aviation test center had once operated. Among the wreckage was what remained of captured Allied aircraft, including at least one B-24 damaged beyond repair by the final bombing raid. The irony was profound and deliberate. American bombers destroying the facility where German engineers had studied captured American bombers to develop better tactics for destroying American bombers. The cycle was complete. The story of captured Liberators in German service represents curious footnote to the larger narrative of strategic bombing campaign over Europe. These aircraft, built in American factories by American workers, flown by American crews on combat missions, shot down or forced down by German forces, then rebuilt and flown by German pilots, served as unique windows into Allied capabilities and American industrial methods. They revealed strengths the Luftwaffe needed to counter through new tactics and weaknesses that could be exploited by skilled pilots. They trained fighter pilots in aircraft recognition and attack procedures that saved lives. They supported special operations missions that achieved tactical objectives. They contributed to German war effort in numerous ways throughout 1943 and 1944. Yet ultimately, they also demonstrated the impossibility of Germany's strategic position by revealing the scale of American industrial capacity. Every hour, German technicians spent maintaining captured American aircraft represented skilled labor diverted from maintaining German aircraft. Every gallon of precious aviation fuel burned testing enemy bombers was fuel unavailable for combat operations. Every bullet fired during evaluation exercises represented ammunition Germany couldn't spare. Meanwhile, American factories produced more B-24s every day, replacing combat losses faster than German fighters could inflict them. The arithmetic was inexorable and unforgiving. Industrial capacity determined strategic outcomes. Technology mattered. Tactics mattered. Pilot skill and courage mattered. But industrial capacity mattered most of all, and in that competition, Germany had already lost before the first captured Liberator arrived at Rechlin. The 1050 caliber machine guns that so impressed German test pilots represented not just defensive armament, but American industrial philosophy, made tangible in metal. Overwhelming firepower through volume of fire. Mutual support through formation tactics. Redundancy through multiple weapon systems covering all approaches, all designed to ensure that enough bombers survived each mission to destroy their targets and return home to fly again. This philosophy worked despite heavy costs. Despite losing nearly 4,000 B-24s to all causes during the war, including combat losses, operational accidents, and weather. Despite casualty rates among bomber crews that exceeded 20% in some units during 1943, despite German fighter opposition that destroyed hundreds of Liberators in determined resistance, the strategic bombing campaign succeeded in its objectives. Germany's war industries were destroyed across the Ruhr and other centres. Its cities burned from incendiary attacks, its transportation networks collapsed under sustained interdiction. And when the war ended in May 1945, American factories were still building B-24s at rates that would have allowed complete replacement of all combat losses within 6 months. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.